This video covers Magnetism 1, Magnetic Fields. So a couple of basics about magnetic fields. Moving charges cause magnetic fields. Magnets have two poles, like you know, that north is analogous to a positive charge in electricity, and south is analogous to a negative charge in electricity. The magnetic field of one magnet applies a force on another magnet. We'll see that in a little bit. The rules of attraction are similar to electricity, that opposites attract, meaning north and south will attract each other, and like poles like north and north or south and south will also repel. So what we're going to do is look at three different types of magnets. Fixed magnets, typical magnets that you're familiar with, bar and horseshoe magnets. Moving charges, such as protons, electrons, and ions. And current-carrying wires, meaning a current consists of many moving charge. Now a little bit about where this magnetism comes from. All substances contain moving electrons in their orbits around the nucleus of the atoms in the substance. However, the way the electrons load the energy levels influences if an atom acts like a magnet or not. So we know that paper is not magnetic. The net magnetism is canceling out. Iron, however, is a well-known magnetic substance, meaning that the net magnetism of all the moving electrons does not cancel out, and each atom of iron is a tiny magnet. But we know that everything that is iron is not magnetic. That means that a piece of iron can be divided into sections called domains. If the atoms or magnets point one way in one section of the magnet and points another way in another section of the magnet, then the magnetism can cancel. If all the atoms in all the sections, or the domains, line up pointing in the same direction, then the iron will become magnetic. Iron can become magnetized by putting it in a magnetic field of another magnet. The other magnet causes the domains to line up. That's one of the most important pieces that we're taking away from this. That the other magnet causes these domains to line up. Now, a magnet can be demagnetized by randomizing the domains again. This can be done by hitting the magnet or heating it, causing the domains to vibrate out of orientation. Now let's look at the field around bar magnets. The magnetic field around a bar magnet is somewhat similar to the electric field between a proton and an electron. So down here we have a picture of a proton, and we have a picture of an electron, and we know that the electric field goes from positive to negative. For magnets, it's very similar. Here you see the north and the south pole. We see that the magnetic field goes from the north to the south. But what's different is that for magnetic fields, they cause loops, which are continuous, whereas electric fields have a beginning and an end. So inside of a bar magnet, the magnetic field runs backwards. It runs from south to north so that you see these loops. So in red, you see the magnetic field inside of the magnet, and then in blue is a magnetic field outside of the magnet. So again, these are continuous loops, whereas in electric fields, they had a beginning and an end. So just like electric fields, magnetic fields are vectors. So what we can do is we can find the direction of the electric field or the magnetic field at a certain point, and you can use vector notation to add all these things up. So remember, in electricity, the field direction was found by using a positive test charge. Well, in magnetism, the field direction is going to be found by using a test magnet. The test magnet in this case is going to be a compass, which is used in navigation to find north. Now, the direction of the magnetic field is the direction that the north needle of a compass would point. So, in all these cases, we're going to look at point P and ask which way it would point, which way a compass would point at those positions. So over here, in our first picture, our compass would point to the left. Here, if we have a north and a south pole, our compass would also point to the left. This is going to be one of the most important situations because this is where we have a very, very strong magnetic field. And then over here, we're going to have, you might need to use superposition, and we'll see an example of that at the end of the video. So what we're going to do is we're going to apply a technique called the right-hand rule. The right-hand rule is used to find the direction of the field around a current-carrying wire. What that means, it's very specific that it's a current-carrying wire. We said at the beginning of this video that a magnetic field is created around a wire that carries current, like we saw in circuits. So we can use the right-hand rule to find the direction of that magnetic field around a current-carrying wire. So for us, the curled fingers are going to point in the direction of the magnetic field lines, and we'll see an example of that in just a second. and the thumb is going to point in the direction of the moving charges or the current. Remember that in circuits, we said by default, current is considered positive in physics, meaning that it's going from the positive plate to the negative plate. We're pretending that protons are moving. So we'll see more examples in just a second. So here we're going to do a couple of examples, and we're asked to find the direction of the magnetic field, which is represented by B, at point P in each scenario. Again, using the right-hand rule, we're going to put our thumb in the direction of the current. So here's our wire. We're going to see our current goes to the right. So our fingers are going to wrap around that wire. And at point P, we can see that our fingers are going into what we call into the page. So we're going to represent this by crosses. So into the page is going to be represented by a cross. And when I say into the page, I literally mean that you are looking down at this paper, and if the wire is going directly to your right and your fingers curl down, it looks like they would go into the paper. So let's look at this next example. Here we have our direction of our current. So our thumb goes in that direction. Our fingers are going to curl around the wire. So at point P in particular, it looks like the magnetic fields or our fingers are coming out of the page. They're coming and pointing in your direction. So we're going to represent that by dots. So a dot is going to represent out of the page. Again, imagine if you're looking at this straight down and your fingers are curling up at you at that particular position. So let's say I was looking at this position instead. At that one position, our fingers are going into the page because again, they're still curling around this wire. So at point P here, they're going back into the page and we see crosses here. This last example, I have my current going in this direction, so our thumb points out in that direction. Our fingers curl around the wire, so at point P, it is coming out of the page. And we're going to represent that again by dots. If I wanted to know the magnetic field at this point P, again, our fingers continue to curl all the way around, so our fingers are going into the page at that point, so that would be more X's. Now this is a slightly different situation. Here we're looking at the magnetic field when the wire is in the Z direction. What that means is you're getting a wire and you're looking down as if it was a pipe and you're trying to look down this pipe. Now if the wire is coming at you, it's difficult for you to say the magnetic field is into or out to because it's actually going in the plane of the page. So what we're going to do is we're going to represent it in terms of clockwise and counterclockwise. So now our dots and X's are going to be representing the wire. So in this situation, we have a dot. That means the wire is coming out at you. So it would appear as protons are coming at you. So if our thumb is pointing in your face, then your fingers are curling around in the counterclockwise direction. In this example, you have the current going away from you, as if protons are moving away from your face. So if that's true, then your thumb points into the page, and your fingers are curling in the clockwise direction. Now to calculate the magnetism for current carrying wires. Again, magnetism or magnetic field is going to be represented by a capital B. It's going to have units of Tesla, so capital T. Here we have a couple of new constants. Mu naught is going to be a constant and represented by 4 pi times 10 to the negative 7. I is current, again, still in amperes. And then R is going to be the distance from the center of the wire, because we can ask to solve for the magnetic field at some point outside of the wire. So this is not the radius of the wire itself. This is a distance away from the center of that wire. Now, if we replace mu naught into our equation, we have a whole bunch of other constants here. So if we put all of that into the calculator, we can essentially get a new constant where we call k prime. And this value is 1 times 10 to the negative 7. This is just another way to simplify this equation. So let's try this first example. Here we have a wire that carries a current of 1.8, Ri. A point P is located 12 millimeters or 0.012 meters away from the wire. So we're asked to solve for the magnitude. Again, you can use any of the two equations, but I'm going to go ahead and use the simplified version. Here, our current is 1.8 amps, and our distance is 0.012 meters away. So I get 3 times 10 to the negative 5. These are units of Teslas. Again, magnetic field is a vector, so it needs magnitude and direction. So this is our magnitude, our numerical value. Again, using the right-hand rule, our fingers go in the direction of the current. Our thumb goes in the direction of the current. Our fingers wrap around the wire. So at point P, the magnetic field comes out of the page. It's coming at you. So again, we represent that by dots. Another way to say this is it comes out in the positive Z direction. Let's say that we had 2 wires instead of just 1. Now these 2 wires carry current as shown in the diagram. That means that one of these currents are going out in this direction and the other current is going out in the other direction. So because magnetic field is a vector, we simply have to solve for the magnetic field created by this current and the magnetic field created by this current at point P, and then add them together, depending on the direction. So let's do the first one. This is going to be in blue. Again, to solve for the magnetic field, it's simply 2 times 1 times 10 to the negative 7 times our current times the distance away. In this case, it's 1 meter. That gives us 4 times 10 to the negative 7. Again, this is magnetic field, so in units of Teslas. For the red one, we want to solve for the magnetic field at point P. I'm going to say the magnetic field due to A. So again, that's 2 times 1 times 10 to the negative 7. Here our current is 4 amps, and our distance is 2 meters. So that is 4 times 10 to the negative 7. Also units of Teslas. Now, before we add them together, we need to make sure they're going at least in the same direction. So if our thumb goes out in this direction and our fingers curl around this wire, at point P, due to B, our magnetic field comes out of the page. So this is going to be represented by dots. Now these are blue dots, so this is the magnetic field due to the blue wire. Then we're going to do the same thing for the red wire. Again, current goes out in this direction. Our fingers curl around the wire. So at point P, our magnetic field also comes out of the page. So if they both come out of the page, they simply add up because they're going in the same direction. So that means our total is simply 4 times 10 to the negative 7 plus 4 times 10 to the negative 7. Again, you need to make sure that you check the direction first, because it is a vector, magnitude, and direction. It is coming out of the page, so that's positive Z direction. And our last situation, here we have 2 wires that carry currents relative to a coordinate axis, as shown in the diagram. Both wires are 1 meter from the origin, so we're going to go ahead and label that information. So the distance from here to here is 1 meter. Here to here is also 1 meter. So we're asked to determine the magnitude and direction of the magnetic field at the origin. Again, what we're looking at are wires. This wire is going into the page. So if it's going into the page, we're going to put our thumb in that direction, down towards the page, and our fingers are going to wrap around it, meaning that my magnetic field goes in this direction. So at the origin, my magnetic field is directly to the left. Now if we look at the red current or the red wire, this wire is coming out at you. It's pointing towards your face. So that means that the direction of the magnetic field is counterclockwise for this one. So at the origin, we're going straight down. So again, if these are vectors and we have a magnitude going in this direction and we have a magnitude going in this direction, I know the sum of those two will be out in this direction. But in order to do that, I need to solve for the magnitude of one, solve for the magnitude of the other, and then Pythagorean theorem. So let's go ahead and do that. Again, that's 2 times 1 times 10 to the negative 7. My current is 2 amps. My distance away is 1 meter. So that's 4 times 10 to the negative 7. For the red one, we have 1 times 10 to the negative 7. We have 1 amp, and we have 1 meter. So that's 2 times 10 to the negative 7. Again, these are Teslas. These are Teslas. And then to find our total at the origin, because these are vectors, we need to Pythagorean theorem. And you get 4.47 times 10 to the negative 7 Teslas. Again, because it's a vector, magnitude and direction. So in order to get direction, we're going to need to do inverse tangent. So we can draw the red vector. We're going to scoot it over. And what I'm going to do is I'm going to solve for this angle instead. So opposite over adjacent, meaning I'm doing red over blue. And you get an angle of 26.6 degrees. Now that angle is only the green portion here. That's not our true angle. Our true angle is 180 plus this value. Because from here to here is 180 degrees, and then we need to add that green portion. So altogether, we should get an angle of about 206.6. Normally we round these to whole numbers, so 207 would work fine.